over 40 tons, a blade that can push through concrete, and in certain configurations, armor built to survive explosions. This is not a tank. It's a bulldozer, the Caterpillar D9. How a commercial earth mover became one of the most extreme heavy-duty machines ever fielded. Caterpillar built the first D9 prototype in 1954, equipping it with a 286 horsepower engine. Series production began in 1955, launching a family of heavy bulldozers designed for sustained earth moving. Early generations brought rapid mechanical development, with the D9E introducing power shift transmissions to handle high torque under load. By 1961, the D9G debuted, serving as the global standard for mining and construction until 1974, followed by the 410 horsepower D9H. A major engineering milestone arrived in 1980 with the D9L. This model introduced the elevated sprocket undercarriage, which raised the final drives away from ground contact shock and reduced drivetrain wear. In 1995, the D9R added differential steering, enabling smooth, continuous turns while maintaining power to both tracks. Modern D9T models now employ an 18-liter C18 diesel engine featuring onboard diagnostics and emissions compliance. Across 7 decades and more than 40,000 deliveries worldwide, this commercial lineage built the solid mechanical foundation needed to support heavy armored modifications. To examine this machine's modern capability, look at the standard commercial Caterpillar D9T. At its heart lies the 18-liter C18 Acer T diesel engine. While this power plant generates a gross output of 487 horsepower, the net power delivered to the flywheel is 436 horsepower. This mechanical force moves an operating weight ranging from 42.8 to 50.5 tons, depending on the chosen attachments. When fitted with a standard semi-universal blade, the vehicle holds 16.6 cubic meters of capacity. This setup allows the operator to cut, gather, carry, and grade massive piles of earth in a single pass. Tracked mobility provides the necessary traction and durability on unstable ground. Power flows through a planetary power shift transmission with 3 forward and 3 reverse ranges, allowing the operator to adjust to changing loads. This configuration prioritizes controlled low-speed force over rapid travel, with speeds topping out around 12 kilometers per hour. A 963-liter fuel tank enables up to 12 hours of continuous operation. In civilian projects, this bulldozer performs large-scale grading, carves road embankments, and clears open-pit mines. Yet, practical limits exist. Moving this 50-ton machine requires specialized heavy transport trailers, and its physical footprint, measuring over 6.6 meters in length, demands substantial turning space. In the late 1960s, the U.S. Army brought the heavy-duty power of the D9G out of commercial yards and deployed it into the jungles of Vietnam. Engineering units required massive earth-moving capability to build supply roads and carve out tactical airstrips from raw, unyielding terrain. The D9G, driven by its 385 horsepower engine, cleared thick tropical forest and dragged down massive trees through sheer weight and low-speed torque. During monsoon seasons, the wide tracks kept the 31-ton machines from sinking into deep, unstable mud. But operating in remote environments created immense logistical burdens, requiring constant supply runs for fuel, heavy spare parts, and transport trailers. These operations remained focused on construction rather than direct fire combat. However, as operators cleared paths while sitting completely exposed in standard open cabs, the environment and the threat of ambush highlighted a major design problem that would shape the future of military bulldozers: crew protection. In the early 1980s, the Israel Defense Forces began adapting commercial Caterpillar bulldozers, treating the modification as a systemic upgrade rather than building a tactical engineering vehicle from scratch. This development peaked in the early 2000s with a standardized protection package designed for the D9R generation. At the center of this upgrade is a fully enclosed, heavy steel operator cabin. Multi-layered ballistic glazing replaces the standard commercial glass, shielding the crew against small arms fire and flying fragments. Distinct from the structural steel used for earth moving, specialized armor plates cover sensitive mechanical zones, including the engine, fuel reserves, and hydraulic reservoirs. Depending on the configuration, some cabins receive overpressure air filtration and internal fire suppression. To counter shape-charged rocket threats, crews install external slat armor designed to disrupt the fuses of incoming projectiles. For active defense, particular vehicles feature roof-mounted machine guns, such as 12.7mm weapons, for immediate force protection. This design creates a layered defense, utilizing the massive front blade as a physical barrier that keeps detonations at a distance. Yet, this protection has clear boundaries. The machine remains susceptible to heavy anti-tank missiles, buried mines, and blast overpressure. A direct hit can still cripple the tracks, leaving the vehicle stationary. Additionally, the extra 15 tons of armor places immense mechanical stress on the chassis, reducing top speeds to around 5 kilometers per hour while sharply increasing fuel consumption. Even with heavy plating, operating a 70-ton machine in a direct fire environment exposes the crew to constant danger. In December 2010, the Mount Carmel forest fire presented a severe civil emergency, prompting the Israel Fire and Rescue Services to coordinate with military engineering teams. The crisis required rapid, heavy earth-moving, and crews deployed a fleet of D9 bulldozers directly into the rugged, burning terrain. Utilizing their massive tracks and high ground clearance, the machines ascended steep, rocky slopes that stopped conventional wheeled fire engines. Operators used the heavy front blades to clear debris, remove fallen trees, and carve out wide fire breaks to halt the advancing flames. While public footage shows armored D9R configurations operating at the scene, the focus remained entirely on opening supply lines and securing safe access routes for emergency personnel. To eliminate human risk in the most hazardous zones, engineering teams adapted the D9 into a remotely operated platform, officially designated the Panda or Thunder of Dawn. This configuration replaces the physical controls inside the cabin with electromechanical actuators linked to an off-board operator station. From a distance of several kilometers, a human pilot controls the steering, throttle, and complex blade hydraulics using real-time video feeds from a 360-degree camera array, thermal sensors, and terrain mapping systems. This setup remains distinct from true autonomy. A human pilot still initiates every single action. While this remote interface removes the operator from immediate blast zones, it introduces clear operational trade-offs. Signal latency can delay control responses, and the lack of a direct cabin perspective limits depth perception. The sensitive electronics also demand more frequent maintenance than standard mechanical parts. As remote technology replaces crew members in hazard zones, this mechanical beast enters a new era. It remains proof that sheer physical force still shapes the modern world. Subscribe for more engineering insights.